illegal? Am I allowed to show you the homework I have to do? Not homework, I guess the books. Am I allowed to show you the books? I really don't know. Need to turn the TV on. Hope my computer can manage all this. I worry about that sometimes. I do not have a supercomputer. Oh, shit. Free education. Yeah. So okay. I looked in a little bit into the law about that, Mike, and the apparent law of any sharing any textbook resource is you are only able to publicly share 10% of the book. So I was thinking, if I stream and only read a chapter, right, at a time, there's no way that that would count as 1/10 of the book. There's no way that I can get in trouble for showing you parts of a book that I'm reading. Because what is the difference between reading a book and putting a camera on that book? I go free Peters. Yeah, so it's just whenever you're teaching, um, there are rules of like if you're instructing someone, you can't. There we go. Yeah, it is a scam though. You're right. It is a scam. I agree. Okay. There we go. There we go. So let's see what our discussions. So we have a couple different answers we have to give to a couple different questions. Also, this course hasn't started yet. I should mention. Um, what chapter I need to go? So this week is Thinker's Learning. So oh my god, chapter 18, and I forgot the other book. I really don't want to read the other book though. It's an extra $50 for a book. Yeah, dude, I always hated that shit when they would assign their own fucking books. You know, like, not this class, but my other class. We actually have a book that was custom made for OU, and so it costs more. Like, they made a textbook edition just for us. Oh my god, how many fucking chapters are there? Let's just start in chapter 18. Which is pretty damn weird. Is there a chapter 18 in there? Okay. Ridiculous. Ridiculous. Put some Spotify on so you're not totally bored. Also, please let me know if it's like the music is too loud. Please always let me know. Usually just listen to Vaporwave or some shit. That might go more this way. No, I think I like mine more. My playlist. If I can find it. Where the fuck is it? Looking for Primeville and chilling. There it is. collection of slow jam instrumentals. I wouldn't expose anything on my account by showing you all this. Like I accidentally show you my password or something. That'd be really sad. Alright, so the first question, we have to finish writing this out. Make sure you know. And this is STD 3513401. So this is the formatting. If I don't know if you guys are actually want to learn anything, this is the formatting you would use for American Psychological Association papers. And I mean, I guess if you just want to have a good paper overall, but you shorten the head. We have an easy acronym, STYK, so that you know Unit 1. Usually I'd put my ID number, but I want you guys seeing that. And this is all just fucking bullshit. None of this matters. This is if you're like truly reporting information and statistical data, but we're not doing that. We just want the format. Also, you can it's page break, but I'm lazy. So first question is, why don't astronomers like being called astrologists? Obviously, that's just a joke question. It's first, assignment. The class hasn't even started yet. To be honest, I like doing shit early. The best way to avoid procrastination is to do shit early. That to me stops me from procrastinating every time. I just do it a week or two early. This starts on the 10th. What is today? The 4th? Oh yeah. Not to suck my own balls, but if you can literally start shit early, your life would be so much easier. Alright, so then I need these guys. So these are the 5 questions we're going to be answering today. We'll do this one assignment, or these 2 assignments, and we'll be probably done. Take about 3 or 4 hours. Because I also got to look up shit, which really pisses me off. But we'll learn together how to look up good stuff. Jesus. What the fuck was that? Why is it indenting like this? I hate this. This is gonna piss me off. There we go. Okay. So this is our discussion question. Everything else. I really don't want this fucking hanging indent, please. Jesus Christ. Microsoft Word still doesn't even work. Oh man. Pisses me off to no end. Doesn't matter. We'll leave it like there. This one's just a joke. This is just a discussion question. I don't really need to look up anything to know how to do that. I do think they want one source, though, or like they want you to course reading. See, how the fuck am I supposed to use an APA citation for this question? You know what I mean? I'm probably just going to use the book. I don't want to have to look up some bullshit about astrology. This is a required elective. Yeah, so this is what they do, and the real reason college is a scam is they'll make you take classes like these, which, granted, very useful for life. Like, I would say I've taken some bullshit classes, like the classes that require you to do like guitar and shit like that. I'm not as big about, but I took a couple of those. Like, those are more bullshit classes. The less bullshit classes are classes like this, where they teach you like shit that's actually relevant. Like this course, if you keep reading on it, is about the function of physics in the universe. They justify this, yeah. Well, this is some of this. These two are very few of the classes I think should actually be required. I think like language should always be required. Chemical, physical, and social understanding of the reality that we live in. So not only psychology, but also understanding the chemical reactions, what happens with physics and weather to make rain happen, how gravity interacts with evaporating water, etc., etc. That is excruciatingly important. Even more so, I think doing extremely advanced shit, like extremely advanced. Like this isn't extremely advanced by any means or anything, but this is beyond, I would say, a high school level introduction to physical science. But I'll read this to you because we actually have to read this. I think we're only reading. Let's see, 511. Do I read the entirety of chapter 18? Big Bang. So that's 34 pages or so, because there's like quizzes or whatever to do. But we're not going to do this. Cat's Eye Nebula, Planetary Nebula, which is a dying star, is gas. We shall not cease from exploration, and the end of all exploring will be an arrival where we start. Okay. The sun will not explode. Years is 13.8 billion years. Yes. So let's make sure we understand our questions. Whenever you're reading, you should always understand the questions. What is the most recent model of standard Big Bang? How does it differ from standard model? Big Bang. How do stars radiate energy? The universe is the totality of all matter, energy, and space. In this chapter, the celestial sphere is defined and used to help describe the locations of the sun, stars, and galaxies, which are giant assemblages of stars and other matter. The techniques used to measure distances to astronomical objects are discussed in Highlight 18.1. Determining astronomical distances after that's like the name of the chapter. After a discussion of stellar life cycles and properties of galaxies, the chapter concludes with a section on cosmology, the branch of astronomy that studies the structure and evolution of the universe. Highlight 18.2, The Age of the Universe, discusses the recent determination of age and composition of the universe. Stars and galaxies emit all types of electromagnetic radiation, including radio waves, microwaves, infrared waves, visible light, ultraviolet rays, X-rays, and gamma rays. Until 1931, astronomers had to rely on information gathered from only one type of electromagnetic radiation, visible light. The advent of radio telescopes led to the discovery of celestial objects such as quasars and pulsars, as well as to the clues about the size and structure of our galaxy, the Milky Way. Most of the radiation of the electromagnetic spectrum, from infrared to gamma rays, is largely absorbed by our atmosphere. Only when balloons, and then satellites and other spacecraft, were able to rise above our atmosphere, did these regions of the spectrum reveal abundant new information about the universe. The result has been a multitude of discoveries and advances, and are presently being made in astronomy unequaled in most other sciences. Some people confuse the science of astronomy with the pseudoscience called astrology. Astrologers contend that the positions of the planets and the sun in the sky at the time of a person's birth affect the individual's personality or future. There are no known forces that could cause such effects. Scientific studies have thoroughly debunked astrology, yet some people continue practicing astrology. So, obviously we got an answer to our first question. So let's bring him up, see what he has to say. Here we go. You can go right here. This closes. Yep, there we go. Alright. So, we have to cite this book correctly. So we're going to go to Purdue Owl because I'm too lazy to type up everything in order. Check. How does the stream sound? Stream sound okay? Am I too loud? Too loud. Maybe you guy. Okay. Got it. Let me. Can't go to the right? What the fuck is going on? We gotta do some shit like this. Introduction to Physical Science. Huh? So it's shipment at all, isn't it? Or can I cite it on here? Sometimes I'll let you cite it on the website. Who the fuck is the author of this book? God damn it. Oh, fucking, here it goes. Ugh. Come on, baby. This is the real annoying part of assignments. It's not even doing the fucking work. It's the stupid little shit like this. Oh, God. Brother. Oh. Jesus Christ, does this textbook not fucking exist? Yo! Alright, that looks like it's the only one. Author James T. Shipman, author Joey T. Wilson, Charles A. Higgins, author Bo Liu, edition 15th, state, year 2019. Gotta view a sponsored message, god damn it. God damn it. Fucking hate. I hate capitalism. I hate it. What info am I missing? God, you's a bitch, motherfucker. No, I'm just doing the. I don't want to do the ebook version. Fuck you. You's a bitch, motherfucker. You trying to play me like no bitch, motherfucker. I guess I could have just copied his, huh? I didn't realize this was an APA. Yeah, I'm just gonna copy his shit. I totally forgot that this counts as APA. So let's go ahead and paste you down there. Hey, buddy. Better. So why don't astronomers like being called astrologists? We can go back. Fuck you. Oh shit. Let's keep the world going. No, they fucking don't. Oh, hey, what are you doing, brother? Oh, I forget this one's weird over here. You have to use all your keybinds, or nothing works. Page 512. So what I usually do is I'll get the information, I'll read through, get the information, I'll come back and retype it all. That's, if you really want to learn anything, that's probably how you should do it. I won't even lie to you. Okay. Okay. Yeah, let's just go ahead and take this one too. Page 512. That'll work. Estimate the total number of stars. I don't care about the facts. I won't even lie to you. This one is the only one that really matters. I won't even lie to you. This one right here. Main sequence star. So black holes form usually from supernovas, right? A view of the stars. Okay. A view of the stars on a clear, dark night makes a deep impression on an observer. Stars appear as bright points of light on a huge overhead dome. As the night passes, the dome of stars appears to move westward as part of the great rotating sphere. The unaided eye is not able to detect any relative motion of the stars on the apparent sphere or to perceive their relative distances from the Earth. The stars all appear to be mounted on a very large sphere within the Earth at its center. Astronomers call this huge imaginary sphere the celestial sphere. Actually, the daily apparent east-to-west motion of the dome of stars is just a reflection of the Earth's real daily west-to-east rotation. Cool. Yeah. I mean, I think everyone knows that, kind of. In the northern hemisphere, the stars seem to rotate around a point of the celestial sphere called the North Celestial Pole. The NCP is the point on the celestial sphere that is the extension of the northern end of the Earth's axis of rotation. At present, a fairly bright star named Polaris lies close to the NCP. Therefore, Polaris is known as the North Star, or Pole Star. Because of the Earth's 26,000-year cycle of precession of its axis, the pole star slowly becomes a different star, and there often is no pole star. The South Celestial Pole is the point on the celestial sphere that is the extension of the southern end of Earth's axis of rotation. At present, there is no South Pole Star. Figure 8.2 shows the celestial equator, which is simply the extension of the Earth's equator onto the celestial sphere. Also shown in Figure 18.2 is the ecliptic, which is the apparent path the Sun traces annually along the celestial sphere. Of course, the Sun does not really move around the Earth, but vice versa. So the ecliptic is really a projection of Earth's orbital plane onto the celestial sphere. Note that the plane of the ecliptic and the plane of the celestial equator intersect each other at an angle. The angle is 23.5, which is the tilt of the Earth's axis of rotation with respect to its orbital plane. The ecliptic and the celestial equator intersect on the celestial sphere at 2 points called equinoxes. When the Sun reaches either point, it is directly over the Earth's equator, and there are approximately 12 hours of daytime and 12 hours of nighttime at all locations on the Earth. Because of the tilt of Earth's axis of rotation, the ecliptic is inclined 23.5 to the celestial equator. The equinoxes are the time and position when and where the Sun reaches the intersection of the ecliptic and celestial equator. The solstices are the northernmost and southernmost overhead positions that the Sun reaches each year. So fun fact, the Earth is closest to the sun during the winter solstice, not the summer solstice. Isn't that crazy? Doesn't that make you want to twerk? As the sun is observed traveling on the ecliptic, it intersects the celestial equator each year approximately on September 22nd, moving southward. This point of intersection is called the autumnal equinox. Autumnal equinox. 6 months later, approximately on March 21st, the sun again crosses the celestial equator, but this time moving northward. This point of intersection is termed the vernal equinox. Two other significant locations lie along the ecliptic between the equinoxes. The point on the ecliptic where the sun is farthest north, approximately on June 21st, is termed the summer solstice, and the point where the sun is farthest south, approximately on December 22nd, is the winter solstice. There are three celestial coordinates associated with the celestial sphere. The half circle that passes through the vernal equinox, the NCP and the SCP defines a celestial prime meridian. It is analogous with the Greenwich prime meridian, defining the reference for designating longitude on the surface of the Earth. The celestial prime meridian currently passes through the constellation Pisces in the sky, but its position is changing very slowly due to the get the fuck on my screen, do the precession. So you have equinoxes, right? You have the rotation at which, the Earth goes around the sun. It's at 23.5 degrees, if assuming that that we are in a plane. The celestial longitude of a star or galaxy is the angle measured eastward along the celestial equator from the celestial prime meridian. It is called the this one is weird. The celestial longitude of a star or galaxy is the angle measured eastward along the celestial equator from the celestial prime meridian. So you have your celestial equator, and then you have an X, you have a Y, and so the celestial longitude is the Z. So you have height, you have length, and you have technical width. I wouldn't even call it width though. You have Z, which is the third plane. Right ascension. The coordinate for measuring the east-west positions of celestial objects. The angle is measured eastward from the vernal equinox in hours, minutes, and seconds. That's another big thing. When you're measuring fucking distance in space, you're using time. You're not using distance. That's one thing I never liked about physics. And why I didn't go into physics is because it's so much conversion. Physics is literally conversion. It's like trying to how do you get apples to equate into Higgs boson units? Which is very difficult. A star's position is described. What about a star's latitude? Celestial latitude is known as a declination, and is simply the angular measure in degrees, minutes, and seconds, north or south of the celestial equator. The celestial equator can be found in the sky by locating the plane that's perpendicular to the celestial poles. This plane currently passes through several constellations, including Orion and Virgo. So, longitude eastward along the celestial equator. So declination, right ascension. That's the vernal equinox. It's hard to tell with just this little picture, but east and west of the prime meridian. So east and west. This is right ascension going this way, and then going up and down of the equator is latitude. Yeah. Alright, so now you all are ready to go point at the stars and know which direction they are. For example, Sirius, the brightest star in the night sky, has celestial coordinates RA 645 and DEC -6 to the 45th, -16 to the 43rd degree. Thus, to locate Sirius in the night sky, you would use its RA and DEC to specify its location on the celestial sphere. Have we gotten any questions? No. Oh, gosh, I'm thirsty. I need some water. Good music, though. This is water, everybody. throat. My throat. When I talk a lot, it gets so scratchy. Alright. I don't care about this. Right ascension has a value of 0 at celestial prime meridian and continues its eastward circle to a maximum of 24 hours. So, the reason we're using... So this is also a fun thing to talk about. As you can tell, like, 24 hours, 360 degrees, all base 6, all base 24, base 12, like, pretty much all of them are going to be, like, base 6. You know, because everything is fucking divisible by 6. Ugh. Base 6. So, RA, right ascension has a value of 0 at celestial prime meridian and continues its eastward circle to a maximum of 24 hours. Okay, yeah, so it's literally just 0, 24. Ooh, God, I love this one too. Everything that's right for me. 1 parsec. Also, what about distance? The distance coordinate is usually measured. This is not important. The mean distance of the Earth from the Sun, yeah, 93 million miles. A light year is traveled by light in 1 year. 6 trillion miles. Right, by the number of seconds in a year. 1 parsec is defined as used to a star when the star exhibits a parallax of 1 second of arc. Whatever the fuck that means. Okay, I completely understand this. 1 parsec is defined as the distance to a star when the star exhibits a parallax of 1 second of arc. Where 1 second is rounded to be 1 of 1. Oh, okay. So, a parallax of 1 second of arc, where 1 second of arc is defined to be 1 of 3,600 of 1 degree. Alright, so it's just a really... What is a parallax? Oh, fuck me. The change in the apparent position of an object relative to more distant object. Okay. The star exhibits a parallax of 1 second of arc. So a change in its positioning, a visible change in its positioning of 1 second of arc. 1 second of arc is trying to be 1 of 3,000 of 1 degree. Huh. Okay. I mean, I kind of get it, I guess. It's just, again though, it's changing time into a measurable unit. That's what physics is. Over and over and over again, you're just exchanging numbers for more numbers. Also, my hair looks so crazy. You're just exchanging numbers and numbers and numbers for more numbers. Over and over and over again until you die. I definitely could have seen myself going into the physics field, but that sounds fucking lame. And like, you know, if you get a physics degree and then you don't get hired, that is much more useless than a fucking psychology degree. Are you kidding me? Like, I feel like a physics degree, if you get a physics degree, you got one job you can do. Physics. You can go teach physics. You can go be a professor. You can do math. Right? You can do a lot of math for people. But it's one job. Physics. Okay. This is not important. Yeah. Physics is very autistic. I think I definitely had the the intelligence for it. I just didn't want to do it. Like, it's just so fucking lame. It's like a nerd. It's like a nerd science. This is if you're like a genius. You're a nerd. You're a fucking nerd. You know what I mean? Like, oh, I need to figure out how far the fucking into universe is. I'm just kidding. I love these. I mean, I love knowing this stuff. Not to be a dick, but now it's cool psychology or chemistry. This apparent motion is called parallax. The angle being measured in the second arc. Blah 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 blah. I don't care. No, I'm never going to calculate the distance to a star my entire life. Wow, he did it. Alright. Because Aristotle and others of his time observed no stellar parallax, they rejected the idea that the Earth moved around the Sun. It was not realized that even the closest stars were much too far away for their parallaxes to be detected with the unaided eye. It was not until 1938 that Friedrich Bessel, a German astronomer, was able to observe stellar parallax using a telescope. It is easy to appreciate why parallax is so difficult to observe. The parallax angle of even the closest stars is equivalent to the diameter of a dime seen at the distance of 6 kilometers. Parallax measurements can only determine the distances to stars that are within about 300 light years of the Earth. So yeah, look, this is literally how it's summed up. Star position on the celestial sphere are given by two angles, right ascension and declination. And it really explained how to get those, but it wasn't that important. So I'm texting a friend back. When I'm in a good mood, I'm fucking incredible at flirting. When I'm not. I'm terrible at flirting. Terrible. Dichotomy. The sun is a star. A self-luminous sphere of hot gas held together by gravity and energized by nuclear reaction at its core. Our closest star is quite large, with a diameter of 100 times the size of the Earth. General information about several of the sun's characteristics is given in Table 18. Dude, I don't fucking care. I've learned about the sun 1,000 times. A cross-sectional view of the sun is shown. Let's begin our discussion. The bright visible surface of the sun is called a photosphere. Okay, dude. I need this stuff. This is the stuff I need. The bright visible surface of the sun is called photosphere. The temperature of the photosphere is about 6,000 Kelvin. Analysis of the sun spectrum shows that its photosphere is composed by mass of about 75% hydrogen, 25% helium, and less than 1% heavier elements. Great. Excuse me. The most abundant being oxygen, carbon, neon, and iron. Iron. Alright. A distinct feature of the sun's surface is the periodic occurrence of sunspots. Sunspots are huge regions of cooler material in the photosphere of the sun where the magnetic field is very intense. A close-up view of the sunspot shows that the photosphere, viewed through a telescope with appropriate filters, has a granular appearance. The granules are hot spots, some 100K hotter than the surrounding surface. They're about the width of the state of Texas. Excuse me. About the width of the state of Texas. It only lasts a few minutes. These granules are actually convection cells that bring thermal energy from the interior to the surface. Figure 18.8 is an image of the whole solar disk. It shows large groups of sunspots. A given sunspot generally lasts for several weeks before disappearing. That's death. Imagine learning what the sun was for the first time, you know? And having to accept that shit. It's like, oh yeah, that giant ball in the sky that gives everything life is not a god. It's just a big ball of fucking fire. Big, hateful ball of fire that fucking hates you. And there's nothing you can do about it other than be sad. You know? I'd be pretty messed up. I mean, I am messed up. But not because of the sun. The number of sunspots appearing on the sun varies over an average 11-year sunspot cycle. Samson, Jesus, go back to your song. Yeah, we are. We're living on the same earth, breathing the same air, eating the same shit. My cycle begins with the appearance of new sunspots near the dude. Oh my god. Listen, bro, I love you, son, but I do not care. The number of sunspots appearing in the sun varies over an average 11-year sunspot cycle. The cycle begins with the appearance of few sunspots near 30-degree latitude in both hemispheres of the sun. The number slowly increases with a maximum generally between 100 and 200 occurs in the middle of the cycle at around 15 latitude. Then the number of spots slowly decreases until the end of the 11 years, which are few near 8 latitude. Sunspot number is graphed versus time, showing the average 11-year period. The previous sunspot minimum occurred in 2009, the maximum occurred in 2014. The next maximum is predicted to occur in 2025. The background blah 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 blah. Wait. Oh, that's actually pretty interesting. Well. Interesting. Alright, the cycle appears to repeat itself, but there is a noticeable difference. Sunspots have magnetic polarity. If a sunspot has a north magnetic pole during the initial increase and decrease, then the next 11-year cycle will show a south magnetic pole associated with the sunspot. Thus, the 11-year sunspot cycle appears to be an aspect of a more fundamental 22-year magnetic cycle. Ooh, man. Fucking magnets. How do they work, man? Other distinct features of the sun's surface are solar flares and prominences. Flares are sudden, bright, explosive events, okay, everyone knows what fucking flares and prominences are enormous filaments of excited gas arching over the surface and extending hundreds of thousands of kilometers upwards. They are evidence of astronomers during the solar eclipse, in which they appeared in great eruptions at the edge of a scoop solar disk. Okay. Above the photosphere is a layer of hot gas, mainly hydrogen, known as the chromosphere. The chromosphere, 6,000 to 25,000 fucking degrees, can be studied during a total solar eclipse, where it can be seen as thin red crescent for only a few seconds during the photosphere is concealed from view. At the time of a total solar eclipse, the photosphere is hidden by the moon, and the sun's outer layer atmosphere, the corona, can be seen as a beautiful, tenuous, white halo extending far beyond the solar disk. The temperature of the corona is about 1 million Kelvin. Astronomers think that the high temperatures of both the chromosphere and corona are due to the transport and release of energy from the intense magnetic fields that permeate the gases, coupled with magnetic fields under the photosphere. The extreme temperature of the corona is sufficient to give protons, electrons, and other ions enough energy to escape the sun's atmosphere. The charged particles are projected into space, giving rise to the solar wind. The solar wind is controlled by the sun's magnetic field, which, actually, that's a good, clan name. The solar wind. It's controlled by the sun's magnetic field, which moves outward with it. These particles in the entrained magnetic field move quickly away from the sun, reaching the Earth in 3 to 5 days. Measurements made by Voyager 1 spacecraft have confirmed that the solar wind and the accompanying magnetic field extend outward to at least 100 AU from the sun's surface. This volume of space over which the solar wind extends is called the heliosphere. What about the sun's interior? The interior of the sun is so hot that neutral atoms do not exist because high-speed collision continually knocks the electrons loose from the atomic nuclei. The interior is composed of nuclei and electrons rapidly moving about more or less independently, similar to a gas. The charged nuclei, ions, and electrons exist as a fourth phase of matter, called plasma. The plasma has an average density of 14,000 kilograms per meter squared, whereas the very core of the sun is 150,000 kilograms per meter squared, which is 150 times greater than the density of water. For us, one of the most important features of the sun is that it radiates energy. However, not until 1938 did scientists understand that the sun radiates energy because of nuclear fusion of hydrogen into helium in its core. Oh my god, fusion. The sun is made up of mostly hydrogen nuclei, or protons, or in nuclear notation, H. At the 15 million Kelvin temperature and extremely high pressure of the core, these protons are moving at very high speeds, and they occasionally fuse together, as shown in figure 18.11. The products of this nuclear fusion are a deuteron, and a proton and a neutron together. A positron, a neutrino, the Greek letter alpha. A neutrino is an elementary particle that has no electrical charge. It travels at nearly the speed of light and hardly ever interacts with other particles such as electrons and protons. Only recently was it determined that neutrinos have mass. Helium, smack them together. Hydrogen, smack them together to make helium. Helium, add another hydrogen, smacks another. These two combined, smacks another. Give you hydrogen, and a fucking isotopic ass helium ion. And the sun's similar. Hydrogen is fused into helium by a series of 3 nuclear reactions shown here in order. Once the deuteron is formed, it quickly reacts with the proton to become a helium-3 nucleus, the emission of gamma ray. Finally, 2 helium nuclei fuse to form more common helium-4 nucleus, and 2 protons. In each of these fusion reactions, energy is liberated by the conversion of mass. These 3 reactions are called the proton-proton chain and can be written as shown in figure 18.111. The first 2 reactions are multiplied by 2. That is, let each happen twice to produce the 2 heliums. Nuclei needed for the third reaction to happen once. And when added together, fuck these fucking parentheses always fuck me up. And added together in an equation for all 3. In the net reaction, 4 protons from a helium nucleus, 2 positrons, 2 neutrinos, and 2 high-energy gamma rays. The high-energy gamma rays are eventually converted into the energy radiated into space. So, this is how it works. This is what we want to do on Earth. You take 2 hydrogen, you smack them together with the power of God, which takes energy. Usually takes energy to do that. A lot of energy. You smack it. You take 2 of these. Right, you smack another fucking energy. I feel like this part, there's different ways to do this. This is the way that suns do it. There's a way to skip this step. Somehow. There's some way to where you can do these 2 at the same time. But you make one of these, you smack another little bit of energy into it, you make one of these guys, you smack these dudes together, you get this dude, so this dude becomes normal, he becomes a regular helium. And then you get 2 of these guys. And this is pure energy. Like you're making energized hydrogen. Mass is converted into energy and conformed with Einstein's equation E equals mc squared. Mass times the speed of light squared. This thing contains about 10 to the 30 kilograms of hydrogen and has been fusing it into helium for about 5 billion years. Every second on the sun's interior, about 6 times 10 to the 11 kilogram of hydrogen is converted into another amount of helium and joules of energy. Even at this rate, the sun is expected to radiate energy from hydrogen fusion for another 5 billion fucking years. The amount of energy that reaches the Earth from the sun is about 1,400 joules per second per square meter. This amount of energy is called the solar constant. Nearly all life on planet Earth is dependent on energy from the sun because this energy controls our total environment. Atmosphere, food supplies, water sources, and so on. A variation in the solar constant as little as 0.5 would have a catastrophic effect on our ability to stay alive. Jesus fucking Christ. Long chapter. Jesus, I have to say. Like the sun, most stars are huge balls of plasma, composed largely of hydrogen along with some helium and a very small percentage of other elements. Nuclear fusion and hydrogen to helium produces most of the enormous energy that stars emit. Their surface temperatures range from 1500 Kelvin to 50,000 Kelvin. Stars vary in mass from about 0.08 to 100 solar masses, but most have a mass between 0.1 and 5 solar masses. A star's size represents a balance between the inward force of gravity and the outward force of thermal and radiation pressure. This condition is called hydrostatic equilibrium. I love that. I love talking about that. If the 2 forces did not balance, then the star would either shrink or expand. The size of the stars vary greatly, and a given star can have different sizes during its lifetime, as we will discuss later. Unlike the sun, most stars are not single stars, but rather are part of multi-star systems. A binary star consists of 2 stars orbiting a common center of mass. Systems of 3 or more stars also exist, but they're not nearly as abundant as binary stars. It's kind of cute. Prominent groups of stars in the night sky appear to be to an Earth observer as distinct patterns. Many of these groups or constellations have names that can be traced back to Babylonian and Greek civilizations, but nearly all cultures have different names for constellations. Although the constellations have no physical significance, modern astronomers find them useful in referring to certain areas of the sky. In 1930, astronomers set specified boundaries for the 88 constellations so as to encompass the complete celestial sphere. Appendix 1 shows the positions of some stars and constellations in the night sky around March and September. The sun has an apparent daily westward motion across the sky, and when the moon is visible, it also has an apparent westward motion. When one observes the stars for 1 or 2 hours, the constellation also appears to move westward across the sky. These apparent daily motions are due to the eastward rotation of the Earth, obvious fuckingly. In addition to their daily motion, the constellations have an annual motion that results from the Earth's revolution around the sun, for example, the planet. Yeah, the fucking constellations move. We need a whole fucking unit on that shit, don't we?
Constellations often have a story, a myth, or associated with them. For example, the bear in Ursa Major, Ursa Minor were said to have such long tails because Zeus had, in a fit of rage, slung them around his head several times by their tails before launching them into the sky. Some familiar groups of stars called asterisms are part of constellations or part of different constellations. The Big Dipper, which is a part of Ursa Major, is an asterium. Another example is the Summer Triangle, which is found in bright star Alta de Nova Vega. Okay, thank you. We still haven't heard anything about main sequence stars. Celestial magnitude. The Hipparchus, the Hipparchus of Nicaea, a Greek astronomer and mathematician, was antiquity's greatest observer of the stars. He measured the celestial location of more than 800 stars and compiled the first star catalog, which was completed in 121 BCE. Hipparchus designed the stars to 6 groups of brightness called magnitudes. The apparent brightness or apparent magnitude of a star is the brightness as observed from the Earth. The brightest ones were listed as stars of the first magnitude, but those not quite as bright were stars of the second magnitude, and so on, down to the 6th magnitude. Which included stars barely visible to the naked eye, blah, 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 blah. Cool. Alright. An extended and modified version of the Hipparchus scale is used today. Alright. Not useful. Oh, God, why? Why? So much useless information. Oh, shit, wait. How do stars radiate energy? Oh, fuck, I probably should have wrote some of that shit down for that one. What page is this? 18. Page. I can't see my keyboard. 18. There we go. No. Oh, wait. Oh, it is. I clicked it. Still the same page, right? Yeah. Very nice. Very nice stuff. Alright. The absolute magnitude of stars are plotted versus the temperature of their photospheres. HR diagram. Okay, dude, yes. This is a rating system. It's just a rating system for stars. White stars radiate how they form, white stars burn out. Stars Astronomers know that stars are born, radiate energy, expand, possibly explode, and then die. Generally, that is a star's life cycle. The exact details depend on a star's mass, and in a minor way, on its composition. The greater the mass of a star, the faster it moves through its life cycle. Gas and dust distributed among the stars are known as the interstellar medium. The gas consists of 75% hydrogen by mass and about 24% helium, along with trace of heavier elements, about 1%. The dust consists primarily of compounds of carbon, iron oxide, silicon, and seem to be distributed uniformly, but instead form cool, dense clouds called the nebulae. There are two major types of nebulae, bright nebulae and dark nebulae. Bright nebulae can be emission nebulae, in which the emission comes from hydrogen. Oxygen and other atoms ionized by the energy from nearby stars. An example of an emission nebula is the Great Nebula in Orion, one of the brightest in the night sky and is closest such nebula to us. On the other hand, some bright nebulae are reflection nebulae, in which the energy of a nearby star is not sufficient to ionize these gases, and the dust just reflects scatters the starlight. Reflection nebulae have a characteristic blue color for the same reason that the Earth's atmosphere makes the sky blue. The Orion Nebula is a bright emission nebula. Blah, 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 blah. Dark nebulae become evident when the starlight is obscured by a relatively dense cloud of interstellar dust. By far the most famous of the dark nebulae is the Horsehead Nebula, also located in the constellation Orion but not visible to the unaided eye. The gigantic dark cloud is framed against the light-emitting region behind it. Its name comes from its shape, which resembles, obviously, a fucking horse. The general evolution of low-mass stars, like our Sun, and stars of even lower mass is plotted on the HR diagram shown in Figure 18.6. The birth of a star begins with the accretion of interstellar material, mostly hydrogen, in large pockets of cold gas and dust within enormous interstellar molecular clouds. The accretion is due to the gravitational attraction between the interstellar material. Radiation pressure from nearby stars and shock waves from exploding stars. The Great Nebula in the Orion is a classic example of a place where stars being born. The size of a star formed in a nebula depends on the total mass available, which also determines the rate of contraction. As the interstellar mass condenses and loses gravitational potential energy, the temperature rises and material gains thermal energy would become known as a protostar. As the protostar continues to decrease in size, the temperature continues to increase, and thermonuclear reaction begins in which hydrogen is converted to helium. At this time, the protostar becomes a star as it is moved into a main sequence. Oh, here it is. As it moves into a main sequence. Okay. There it is. So, maybe I did have to read the other page then. A little bit more. Aha, I did. Alright, here it is. Alright. Most stars enter from the trend which by stars. These stars form the main sequence. From the lower right, most stars. Pages 521. Okay, to which part star? These stars in our band going from the lower right. Color stars are direct correlation to its photosphere. The hottest stars in the range are blue, whereas close to its are red. Between the extremes that are white, yellow, and orange. Stars above. Isn't it weird that the hottest stars are just blue? It's such a weird thing. So this is the HR diagram. stratosphere. I'm pretty sure every question it has to be 250 words, apparently. How do they form? What is the main sequence? No reactions occur within them. Jesus fucking Christ. Mm-hmm. And there is where does the name come from? I don't fucking know. Oh, I guess does it just come from the HR guy? I guess this is asking that. So the story never different multiplied by the protos star. As hydrogen in the star's core is converted to helium, the core begins to contract. It starts with after the next sequence. Fuse hydrogen and helium. Ooh. Okay. As hydrogen in the star's core is converted into helium, the core begins to contract and heat up. This process heats the surrounding shell of hydrogen and causes the fusion of the hydrogen in the shell to proceed more rapidly. The rapid release of energy upsets the pressure gravity force balance and causes the star to expand, cool down, and enter the red giant phase of evolution. It now moves off the main sequence as shown in Figure 18. But I feel like a lot of this is just basic stuff. Because the sun has a fuel supply of one solar mass star, it is expected to become a red giant in about 5 billion years. The sun becomes so large that it will engulf the orbits of Mercury, Venus, and probably the Earth. Betelgeuse, a well-known red supergiant in the constellation Orion, is that it was so large, if it were placed where the sun is located, it would extend out nearly to the orbit of Jupiter. Jesus Christ. It's impossible to comprehend that truly. Eventually, the core of a red giant gets so hot that helium can fuse into carbon, and if the star's mass is great enough, then other nuclear reactions will soon occur, which heavier nuclei may be created. The creation of nuclei and elements inside stars is known as nucleosynthesis. If a star is a high-mass red supergiant, the nucleosynthesis can continue all the way up to the element iron, which is the most stable nucleus. During the red giant phase, a star varies in temperature and brightness. It becomes a variable star for a relatively short time, and its position on the HR diagram moves to the left. The star becomes very unstable, and the outer layers are blown off, forming a beautiful planetary nebula. The chapter opening photo is also a planetary nebula, appropriately named the Cat's Eye Nebula. It is 3,000 light years from the Earth and 0.5 light years in diameter. Despite its name, a planetary nebula was absolutely nothing to do with the planets. The name came from William Herschel because he thought they looked like his newly discovered planet, Uranus. Figure 18.16 shows the position of a star expanding a planetary nebula on the HR diagram. The shell of expelled matter diffuses into space over a period of about 50,000 years and provides material from which new stars may eventually form. Our sun is thought to be a second or third generation star, being composed partially of elements ejected into space by stars that have lived and died before the birth of the sun. The remaining core of the planetary nebula is now a white dwarf, in which fusion no longer occurs, and the star slowly radiates its residual energy into space as it cools. When a star becomes a white dwarf, it gets very small. It has gravitationally collapsed to the smallest possible size at which the force of gravity is offset by the repulsive force of electrons in each atom. The star is about the size of the Earth and is so dense that a single teaspoon of matter may weigh about 5 tons. Because it is not very bright, it is low on the HR diagram. Many white dwarfs in our galaxy have been identified, and one of the best known is related to the bright star Sirius. Actually, Sirius is a binary star system composed of a spectral class A main sequence star, Sirius A, and a companion white dwarf, Sirius B. Sirius B is approximately the size of Earth but has the mass of the Sun. Its photosphere temperature is about 25,000 Kelvin. Weird. Sirius is a binary. What if a protostar does not have enough mass for sustained fusion to occur? Astronomers theorized for many years that failed stars named brown dwarfs must exist. They realized that brown dwarfs would be very dim and hard to find, probably showing up only on the infrared radiation they emit. The brown dwarf of Gliese 229b was the first to be found in 1995. Since then, hundreds of brown dwarfs have been identified, and astronomers think that galaxies might be teeming with more. Could Jupiter have become a star, forming a binary star system with the Sun? No. Jupiter's mass is only 1/1000th that of the Sun. A gas giant would have needed at least 80 times more mass before it could become a star. Such is the life cycle of low-mass stars. Protostar, main sequence star, red giant, planetary nebula, and finally, with the universe thought to only be 14 billion years old, not many of the low-mass stars have had time to evolve into white dwarfs. High-mass stars have had a different life cycle, which we will see in chapter 18.5. Jesus fucking Christ. Man, this is really, really boring. I hate having to read about this shit. This is why I couldn't do physics, man. It's just like, okay, awesome. Half of the stuff is not that important. Let me summarize in like 10 minutes. Here we go. Many stars appear dim and insignificant, but suddenly, in a matter of hours, increase in brightness by a factor of 100 to millions. A star undergoing such a drastic increase in brightness is called a nova, or new star. A nova is a result of a nuclear explosion on the surface of a white dwarf. An explosion caused by relatively small amounts of matter falling onto its surface from the atmosphere of a larger binary companion. A nova is a hot new star, is not a new star, but rather a faint white dwarf that temporarily increases in brightness. Sometimes stars explode catastrophically and throw off large amounts of material and radiation, and increasing in brightness. Because psychology, you're learning a lot about like real people. Like, it's everything you learn in psychology is immediately going to be useful. Everything. Like, some stuff there is like research is still going to be done on, but everything in psychology can immediately be used. Like, because what are you learning about in psychology? Relationships between people and their parents, how to handle hard situations, how trauma affects you, right? How abnormal psychology issues can be treated and managed and viewed through a scientific way. So I think psychology is just so much more fun. Even chemistry is more fun than this shit. Because again, you immediately get to use it. It's like, okay, I'm learning what lithium is, why lithium is able to be swallowed by humans and also used in batteries, right? Like, that's useful stuff, you know? Like, how much lithium will kill you, you know? And like, all it takes is one different fucking ion. All it takes is one extra electron, and suddenly that lithium becomes fucking poison, and it kills you instantly if you take it. That is very interesting, how something so tiny, something microscopically insignificant can literally change if you die or not. Just one tiny little electron, one unit of energy will change if you die or not. Same thing with sodium gated ions, same thing with chlorine gas, mustard gas, cyanide, everything. Sometimes stars explode catastrophically and throw blah 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 blah. White dwarf. A type 2 supernova results in the collapse of an iron core of a massive red supergiant. This type of supernova leaves behind either a neutron star or a black hole. Both types scattered their original matter to space and machine by spectra. Type 2 supernova shows hydrogen spectral lines from the red supergiant, and Type 1a shows carbon spectral lines from the white dwarf. Fewer than a dozen supernovae and their remnants have been recorded in the Milky Way galaxy. The best known is the Crab Nebula and the constellation Taurus. By knowing the Crab Nebula's average angular radius and expansion rate, the original time of the explosion can be calculated. The result agrees closely with Chinese and Japanese records that report the appearance of a bright new star in the constellation Taurus in 1054 CE. Reportedly, the supernova was so bright that for 2 weeks it was possible to read at night by its light. Oh wow. Yeah, that might cause some fucking spiritual belief, you know what I mean? The Crab Nebula is... oh, fuck, I don't care. In 1987, a supernova was observed in the Large Magellanic Cloud. It is the first supernova to have been observed in the LMC, which is at 180,000 light years away. It is the third closest galaxy to our Milky Way. The supernova was designated 19878. The discovery of supernova 19878 was important to astronomers because they could at least observe a stellar explosion from the beginning. They can now observe the remnant star and track what happens to the debris coming from the explosion. Since 1987, valuable information has been obtained from supernova 1870 behind the James telescope. Okay, awesome. Many thanks, many applause. After we get the answers to number 3, we're going to stop reading this chapter because I do not give a shit. And a little bit more on number 2. Everything else is pretty basic though. Type 2 supernova results when high mass... This page is not too long. As you have learned, Type 2 supernova result when high mass stars develop into supergiants. When supergiants' nuclear fuel is depleted enough, the interior can undergo a sudden, catastrophic implosion to form a small diameter neutron star. During the implosion, the outer layers of the star bounce off the rigid inner core and explode into space, giving rise to the supernova and leaving behind a small core during the explosion of a supernova. The energy and neutrons emitted cause the nucleosynthesis of elements heavier than iron. Except for the primordial present from the star hydrogen and helium atoms, and some lithium, all the elements up to and including iron are thought to be made during the normal fusion processes in stars of various masses. All elements more massive than iron are thought to be originated in supernova explosions. Thus, the elements scattered into space during explosions of supernova, novae, and planetary nebulae provides the material for future generations of stars, planets, moons, and so forth. Carl Sagan, a famous American astronomer, was fond of saying that they are made of star stuff, and scientists think he was right. The core of a Type 2 supernova may collapse to approximately 10 kilometers in diameter, the size of a small city. The electrons and protons in this superdense star combine to form neutrons, hence the name neutron star, that have enormous density, equal to that of a nucleus of an atom. If you think of a white dwarf, just so you know, electrons carry a negative charge, neutrons carry no charge. Electrons are like 1/millionth the size of, maybe not millionth, maybe like 1 in 100,000th the size, the weight of a proton. So, to get your electrons to have the density of a nucleus of an atom, it's pretty damn crazy. If you think a white dwarf is dense at least 5 times a teaspoon, then consider a teaspoon of a neutron star might weigh about 1 billion tons. Because the angular momentum of the original star must be conversed, the small size of a neutron star dictates that it must be spinning rapidly. Rapidly rotating neutron stars seem to emit radio wave pulses. These stars are called pulsars. When pulses are detected and measured on the Earth by large radio telescopes, such as the Very Large Array in New Mexico, hundreds of pulsars have been identified since the first one was discovered in 1969. The waves from a specific pulsar have a near constant period that may be between 0.002 and 4 seconds. One of the most rapidly spinning pulsars, or neutron stars, is located at the middle of the Crab Nebula. The remnant of the supernova 1052 solar period is and emits pulses not only. So that means it rotates this fast. For every 0.003 seconds, it rotates once, right? And it's like assuming at least 12 kilometers in diameter. So that's really fucking fast. That's like, we can't even really think of it because it's so fucking quickly. Like it's moving so fast. I can't even think of anything to compare it to. You know, like there's nothing on Earth that's anywhere near as fast. It's like faster than the speed of light almost. Except the speed of light I think is 0.0006. Right, so it's literally a half a magnitude away from being the speed of light. Or 0.0005, I can't remember. Doesn't matter. This apparent pulsation can periodically send a beam of radiation along the magnetic axis toward the Earth. Blah, 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 blah. Oh, God, it's so much, it's so fucking much. As dense as neutron stars rise, do not represent the ultimate compression. If the core remaining after supernova explosion is greater than about 3 times the mass of the Sun, then theory predicts that it will end up as a gravitationally collapsed object even smaller and denser than a neutron star, an object called a black hole. It is so dense that even light cannot escape from its surface because of the object's intense gravitational field. By Einstein's theory of general relativity, gravity affects the propagation of light. A black hole represents gravity's final victory over all other forces. Yes. In a black hole, the star's matter continues to contract until the original volume becomes a fantastically dense point called a singularity. The singularity is surrounded... Oh, wait. I already know what the event horizon is. Describe the characteristics, though. 'It's kind of basic knowledge about black holes. Pages and stuff. 526. 526, perfect. Listen, man. Black hole stars matter continues to contract until the original volume becomes a fantastically dense point called a singularity. Radiation within the event horizon. The size of a known rotating black hole, called the Schwarzschild radius, named after German astronomer Karl Schwarzschild, who first calculated it, is the radial distance that the event horizon located from the singularity. Calculation of the event horizon for a black hole with a mass equal to the Sun uses a social radius about like. Okay. Because most stars rotate. Wait, is the event horizon is the point at which light can't escape? Fuck, what kind of spell? pages aren't actual pages. So you like go to the next page, you're not actually going to the next page. Oh gosh. Mouse. Closer to me. Jesus Christ. Jesus Christ. Albert Einstein predicted the existence of gravity waves in 1916, but indirect proof of their existence came almost 60 years later when a binary pulsar was detected. These orbiting fast-spinning neutron stars decayed according to general relativity and mass energy of emitted gravity waves. However, it would take 99 years before they were observed directly. In 2015, Laser Interferometer Gravitational Wave Observatory detected gravity waves from two black holes crashing into one another. What are gravity waves? Gravity waves are distortions in space-time caused by massive objects moving fast during extremely high. All massive objects like stars, galaxies, and black holes spin space-time. That effect is shown in 1919 as a deflection of light from a distant star that passed close to the sun during a total solar eclipse. Stationary or slow-moving massive objects have a near constant gravity field and thus do not emit gravity waves that are detectable. Gravity waves are non-electromagnetic waves like visible light, X-rays, or radio waves. They are distortions in gravity because these gravity waves come from extremely energetic events, and because they can travel nearly unimpeded across the universe, they're an incredibly new way to study the universe. For example, the 2015 LIGO detection was calculated to come from two merging black holes about 1.3 billion light years away. Interferometry is a clever but familiar experiment used to detect gravity waves, widely used in optics. An interferometer splits a light beam into two perpendicular beams and measures constructive and destructive interference. Early interferometry experiments also determined the speed of light and showed evidence for Einstein's theory of relativity. Okay, this isn't really answering any of this. Ancient people thought that the broad band of stars across the dark night resembled a trail of spilled milk. This broad band is observed with the viewer looking to the plane of the galactic disk and sees an abundance of stars too small to be seen individually. The Milky Way consists of 100 billion to 200 billion stars and has three basic parts. The crowded center called the nuclear bulge, the thin plane containing the spiral arms called the disk, and the spherical distribution of stars. Okay, wait. The star at the middle of our universe, or the black hole, is Sagittarius A, if I remember correctly. The thin plane containing the spiral arms called the disk, and the spherical distribution of our star cluster with a halo. Yeah. Our nuclear bulge. Supermassive magnetic exists in the core Milky Way, such as a hypothesis, high velocity. Yeah. So I'm going to use a global consortium of Earth-based radio telescopes to synthesize the first ever image of a supermassive black hole, lying at the center of galaxy M87 and 55 million light years distant. The black hole has a core mass of 6.5 billion solar masses, more than 1,500 times larger than the core mass of the Milky Way. Gravity is so enormous around the core that nearby light is bent into a ring, exposing the supermassive black hole at the center. I feel like I'm going back in pages. You know what I mean? Like, what the fuck is this? You're like remembering all of this. Well, I mean, okay. I know half of this shit. You can ask me anything about what we just talked about. I remember literally this stuff is basic stuff. Like, I just told you the name of the black hole at the center of our galaxy. Like, this isn't important, you know, none of this is important. Like, usually when you do this for like 5 years, you kind of like discern the valuable information. I think that's what truly makes a good note taker, is what information can you discern is that is useless. It's like a lot of this is useless. It's just stuff they put in here to get the minimum page requirement of a fucking textbook. Pisses me off to no end. Like classification of galaxies. When are you ever going to classify a galaxy, brother? I just don't care. And if I wasn't reading this out loud, I'd be done already, you know what I mean? No, I don't care, but I read in my head 10 times faster than I can read. I could see if I was... Let's see some... Yeah, see, it was red flash. I don't care. Alright, escape velocity, blah, 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 blah. Plays ours. Midterm, then forget about it. Yeah, I don't know. I remember most of the stuff I've learned in my life. Like if you ask me a question, I would say there's like a 7 out of 10 chance I'll know the answer if I've learned it before. Linear scope with high resolution. Oh God, I don't fucking care. Good song. Oh. What does he know? Oh, he's like, can you only see this? On my screen, you can only see this document, right? Huh, I didn't even realize that. On my screen, I have my other document open. Yeah, again, it's just talking about... Oh, God. See one browser of textbook page. Yeah. I figured, and then you can see this, but you can't see the other side of my screen. I have another screen over. I have my notes on. Ugh! Oh, my booty. Oh. I'm so tired of reading about the fucking space. I'm also just hungry. But hungry for what? Hungry for apples? Probably just make a smoothie, honestly. Probably just make a smoothie. I think it's so hard for me to accept that I'm happy. You know what I mean, Mike? Like, I feel like my brain, whenever I think, like, for a moment, like, I'm very content with my life. Like, my brain will not accept it. It's like it's hard to accept happiness. You know what I mean? Like, I truly do enjoy learning. I love it. I'm addicted to it. I don't know what it is. I just like learning stuff. That's all I want to do is learn stuff and teach people. It's like a deep, deep passion I have ever since I was a little tot. Just an idea. Ever since I was just an idea, I've loved teaching and learning. And it's hard. I think it's just the depression, dude. I think I'm just depressed. Because, like, I know I'm happy. I know for a fact that I'm happy. And I'm content with what I have. And then I'm gonna be okay regardless. But that deep internal anxiety never goes away, huh? That deep internal feeling that you are not happy. That you need something else. I don't know. I don't know, Mike. Ugh. Let's see. Let's text back all women. I wish I could just like put you on my phone real quick, just to show my phone screen. Damn, this bitch says she spends $1,000 on food every month. How are you spending $1,000 on food? As a woman and her child. Okay, ordering DoorDash probably. Yeah, honestly. I spend, compared with that, she lives in the same town I do. I spend about $300 on groceries every month. But again, I'm a lot bigger than this woman is. And I still don't consume that. I still eat out. I eat out like once a week at least, you know? Once or two times a week. Look at that belly. Work so hard on that. I've never had a belly. It's very nice. You know what I mean? I've always been like boned. You can see my ribs skinny. It's very nice to have a stomach. Yeah, I'm very frugal. I mean, I was raised poor as shit. Man, bro. I guess the camera always makes you look different. I swear. Like, sometimes it just shows off on my scars. Like, I can see my scars on my screen. I can see my bony ass knuckles and oh man, my ripped ass forearms. It's weird as fuck. It's like some angles you look so chubby, and some angles like it's like oh shit. You look nothing like you remember yourself looking like as a kid. You know, it's like holy shit. You're just suddenly big and muscular one day after trying so hard for so long. Oh, it still trips me out. I think it's just body dysmorphia from being a little poverty baby. But now here I am, full of muscles, full of muscle and fat. And I'd kill a man for a fucking Klondike bar. What would you do for a Klondike bar? Genocide. Okay. Where's my cursor? Dark matter. Analysis of orbital speed. Stars and great intakes that it contains much more mass. Be a communist streamer? What is a communist streamer? How do you even do that? And we need to restructure. Honestly, I think I'm done reading this today. We have everything except the 3. I'll finish the rest tomorrow. Because I'm tired of doing this so much. At least, no, I need to get the number 3. I can't just give up. I need the number 3. Socialism. See, the issue, here we go. So after this should be it. Is the branch line, it's a structure and evolution of the universe. Something was determined. Let me finish this and we'll talk about all that. This is the last thing I need. And we're done with the studying because this is the most boring book I've ever had to read in my life. Astronomers determine the structure of the universe by detecting and analyzing electromagnetic waves from galaxies. Okay. Some great songs today. Are the songs alright, Mike? Can you hear them alright? Like, are they loud enough or no? I'm saying, can you hear it alright? This is a good song. I'm an old-fashioned turntable type of guy. I love a good cut on a fucking disc. Throw me a good cut on the disc, I'll fucking listen to it. I don't care. Actually, I do care. I'm not gonna lie. Get the fuck away from me. This. that's always interesting to talk about, has nearly zero curvature. And which goes to key in Einstein's theory that we exist on a plane, that everything is flat, and that there is only 3D to the human brain because of gravity and the interaction of the fundamental forces. You know, so remember that. Jesus Christ. I need y'all to please sit on the left side of the fucking map. Thank you. Well, goes is that 10 to the negative 5. Oh shit, what page is this? Oh fuck. I didn't put the fucking page down. I think there's 539. Page 539 and page 540. Page 539. Huh? Am I still here? My Xbox fucked up. Fuck. There we go. Happens in what ways? Okay. Yeah, so again, like all of this stuff I knew. I just didn't want to. Like, the main reason I'm reading it is to make sure I'm not missing any new information. But yeah, pretty much, the summation of the dawn of the universe is that before its conception, we have no fucking idea. It's hypothesized that there was a time when everything was so hot and bound together, everything was so close, was so tight and so hot that the laws of physics didn't exist yet. Only when things cooled down enough that hydrogen and helium, like everything is gas. The very first thing that happened was that everything is really hot, everything is gas. That gas bounces around until it cools down, and then it combines, creates the first atoms and everything. Because you got quarks and stuff, you know, that exist, and so they combine. You have you have your two positive and your one negative quark, right? And that creates the electrons, protons, and neutrons. Those guys get together, make helium. Hydrogen. Hydrogen gets together, makes helium. Then you have your first stars, hydrogen, helium, gas stars. Your stars explode, make more shit, combine over and over again. Very simple. Very, very simple. Hey, we did it. Celebration. Celebration time. Jeez, it only took like an hour and a half, too. That was pretty good. Pretty good time. Pretty good time, all things considered. Now let's see, what's this? A blank. A rapidly rotating superdense core. Left. A rapidly rotating superdense core left over at the end of the life of a high mass star. That's a neutron star. This is another word for it. mysterious energy that seems to be causing the expansion of the universe to accelerate. Is that dark energy or dark matter? Yeah. Astronomers use this distance when measuring the parallax of a star. That's a parsec. A shell of matter ejected from a variable star later. A shell of matter ejected from a variable star later in its life. That not just. What is it asking me? A shell of matter ejected from a variable star late in its life. A shell of matter. That's a nebula. It's a nebula, isn't it? I'm not sure what else they're asking me. The apparent path the sun traces annually on the celestial sphere. That is ecliptic. Large groups of stars found in a spherical halo around the Milky Way. Ooh, large groups of stars found in a spherical halo. Is that not just a cluster? The planetary nebulae? Or the globular cluster? Let's see. Stars found in spherical. Okay, let's see what F is. Neutron star, dark energy, parsec, planetary nebula, and then ecliptic is right. Globular cluster. I guess that one was half right. I got that one half right. The name given to all matter, energy in space. What? Matter? Universe. These small, hot, dense stars are the fate of low-mass stars. These are white dwarfs. The brightness of celestial object as observed from Earth. Ooh, that is apparent magnitude. As observed from Earth. The mysterious unseen matter that accounts. That's dark matter. The other one was dark energy, now it's dark matter. Primordial radiation that resulted from the Big Bang and fills the entire universe. Primordial radiation. Cosmic microwave background radiation. The brightness. Primordial radiation that resulted from the Big Bang and fills the entire. Did that? Wait. Yeah, no, I said that. Wait, did I? Yeah, okay. The longitude coordinate celestial sphere, that is right ascension. And then the narrow band of stars going from upper left to lower right in the HRS main sequence. The event when it started at supernova, large cool stars to the upper left. Was it red? Red giants? And then the latitude coordinate, that is declination. So much. The visible layer of the sun, that's photosphere? Or is that. The photosphere. The event when it's talking about the blue, that's supernova. Alpha Versailles. The relationship between the distance of a galaxy and its recessional velocity. Cosmology? Or is that absolute magnitude? The brightest star would have a distance of. That's just an object so dense that its singularity means it's a black hole. Our best theory to explain the temperature composition, that's Big Bang. The huge imaginary dome, celestial dome, whatever the fuck it's called, celestial sphere. The branch of astronomy that studies the structure and evolution of the universe. Cosmology. An extreme large collection of stars held together by gravity, star cluster. A sudden brightening of the light to a star due to explosion of accreting material. just a nova. There's a nova and then a supernova. The graph H used. The graph. Oh fuck. Sudden brightening of a star is the explosion of chemia. The graph used to plot the temperature in D and absolute magnitude of stars. Is that the Hubble-Richter law? Or the HR diagram? The HR diagram. The emission, reflection, or dark clouds of gas. Emission, reflection, or dark clouds of gas and dust in space. I'm not sure I understand this question. Emission, reflection, or dark clouds of gas and dust. Is that not relationship? Is that not just nebula, black hole, galaxy? Oh, is that just galaxy? No. The other one, that one earlier must have been galaxy, so that one has to be either cluster or nebulae. Some of these are a little tricky. Like they could be like, I feel like they're almost interchangeable. Relation between the distance of a galaxy and its recessional velocity. The relation between the distance of a galaxy and its recessional velocity. Absolute magnitude. Let's check our answers. Nebula, ecliptic. Yeah. 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 No, I got that one wrong. It's one wrong. We'll count that one as wrong too, because like I knew it was one of the. I knew it was one of three. Get that one right. That's 19. Get that one right. Get that one right. Yeah. Okay. Yeah. Yeah. All right. Pretty good. What is the point of such a What is the point of such a sphere representing the extension of the axis of the North Pole? What is the point on the celestial sphere representing the extension of the axis of the North Pole? Is it not just A? Yeah, okay. What is the name of the path in the sky that the sun appears to follow? The ecliptic. The angular measure in degrees south of north or south. That right ascension. C. Ah, fuck. Declination. Fuck. I knew that. Damn. North or south is declination. East and west is right ascension. Which is the longest part of the interior of the sun. Photosphere is the outer spot. That's out. It's radiation zone or corona. I'm gonna go with B. Yeah. Why is the dark energy of the sun? They're hotter than the material around them. Let's see. Oh, D. Fuck. I knew it was D. Come on. Where in the sun does fusion of hydrogen occur? Only in the core. Yeah. And the part of the sun structure that we see in visible light is which of the following? Oh, okay. The part of the sun structure that we see, that is chromosphere. Fuck, photosphere. Fuck, I knew it was one of those two. I could have sworn. Okay, for some reason I thought I was talking about during the fucking eclipse, but yeah, okay. Obviously the outermost layer is going to be where the visible light is coming from, the fucking photosphere. Forgive me. What force keeps all the stars from flying apart? It's gravity. Check the answer. No, probably classifies a star based on its temperature. Ooh, which probably classifies a star based on its temperature. Spectral type. I really have no Relatively cool stars. The following stars, it is red or white. Wait. It's both of those. No, it's red. Yeah, red. When the sun becomes a red giant, about how big will it get? Fucking 100. Oh yeah. The reddish color in the famous Orion Nebula is which of the following? It is an emission. Yep. A white dwarf has about the same diameter as which of the following? Texas. Oh nope, the Earth. Fuck. Sunspots are the size of Texas. Damn it. What is the fundamental quantity of a star that indicates its ultimate fate? Mass. Which event is believed to create elements heavier than iron? Supernova. Black holes appear basic for what reason? Appear black. Oh wait. Light cannot escape them. Liquid is classified as okay. Spiral. How long does it take light to travel to the diameter? 18,000 years? 100,000. Fuck. I knew it was way more than 1,000. I didn't know if it was one of these two. 100,000. Key observations to light telescope for the universe is expanding. I'm gonna say, ooh. Got that wrong? Look at that wrong. The light energy remnants of the explosion. Which I was gonna say A on that one. What is the cosmic background radiation? Oh, cosmic light remnants of the explosion. It's A. Yes. Yes. Oh. I'm not doing the film thing. Fuck that. Oh. Alright. I always like doing a little quiz at the end though. I enjoy that. Oh. And just to prove that I retain almost all the information of shit I read. I don't know if it's just a me thing or it's because I've practiced reading for so many years in my life. But as I've literally just proven, I remember about 70%. I missed 3 questions. I missed about, 20% of the question. Like 13%. So, yeah, I'm right back. I'm going to go poo.
free. Little poopy butt. Little poopy butt free. Oh. Poopy, 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 poopy butt. Alright, we'll finish the rest of this later. Because I can't even do it. I can't even turn it in. I can't even. Well, now what do I do with my life? I should eat something. Oh, I should eat something. Let's get some food. But what? A smoothie? A smoothie? It'd be good for me. Eat a smoothie. In the rate of a samurai. Come with me like usual. Some days, some nights, there we go. Some live, some die in the way of the samurai. Some sun up to sundown. Wait on the battle cry. Battle cry. Battle cry. I'm not sure what I want to make. I'm not sure. But I wish I I'm making chicken alfredo with broccoli. Broccoli. Nice. I have all the ingredients for that too. Except the cream, I didn't get heavy cream. Now you get to see the true size of my arms in the kitchen. Oh gosh. Oh, so great. Back of my arm though is like fucked up. Like you can't hear it every time like I put my arm down, it pops. And my left arm, funny enough, is smaller than my right. But this one is like twice as strong. It's just so dense. You know, it's like hitting bone. Weird seeing myself. I always get freaked out. I'm like, oh, I exist. Oh. I need to use that rice before it goes bad. Rice. I need to use the rice, but I have no meat. Oh, I can make shrimp fried rice. Shrimp fried rice for breakfast, though. I don't know, it's more of a dinner meal. Oh, I don't know, that's pretty lazy. I need to eat my eggs, too. Need to eat my egg. Oh shit, I'll see you to change. Cooking. Making love. Oh wait. Making love.
Dick bitch that guy?